Okay, cool. Okay, so hi everyone. Thank you for inviting me to present my work. So in this talk, I will present work that I did in my previous postdoc on bias and generalization of foundation model for breast mammography across datasets. And it's a paper that has been presented at MICCAI this year, and that was also early accepted at MICCAI. So our goal in this paper was to understand how foundation models behave when they are applied on data from specific populations, but also more broadly. Mammography is a key imaging modality for breast cancer screening and diagnosis. And recently there has been a strong push to use machine and deep learning models to extract imaging biomarkers from mammography, but also from MRI. And the models that are used for cancer detection or classification, breast density estimation, but also for many other tasks. But the datasets on which they are trained, they are rarely representative of the global screening population. They are often drawn from specific countries, hospital devices, and many populations are underrepresented. And this situation can lead to biased models with spurious correlations and poor generalization when applied to new settings. And at the same time, we now have large foundation models that are pre-trained on huge datasets with self-supervisions. And these models are becoming standard backbones in medical imaging. And the hope is that they generalize and transfer well. But we still don't fully understand how bias and generalization issues look in this setting. So this leads to two main challenges that we found about foundation models. So first, these foundation models can inherit and amplify biases present in their pre-training data, and they can capture spurious correlations that are not related to clinical tasks. And the second question was, well, the second challenge was that they may still generalize poorly across datasets unless they are extensively fine-tuned, which is actually not always feasible, especially in low-resource settings. So in this work, we focused on a simple practical scenario. We kept the foundation models frozen and we trained only linear classifiers on top of the features extracted from the foundation models. And we were interested in two questions. How do bias and generalization issues manifest in these linear classifiers? And what strategies can we use to mitigate potential biases and improve fairness in a frozen feature setting? So to do this, we gathered multiple public but also institutional mammography datasets from all over the world. So we obtained data from North America, Europe, Middle East, Asia, and together these datasets, they cover diverse patient population, devices, but also acquisition protocols, and most of all, disease prevalence. And on the model side, we had a look at 5 foundation models. Some are pre-trained directly on mammogram, such as MammoClip. Others are pre-trained on medical images more broadly. So here it was Gloria and MedClip, and they were mostly pre-trained on chest X-ray images. And we also had a look at 2 foundation models pre-trained on natural images, DynoV2 and CLIP. And so, as I said before, all models are used as frozen feature encoders, and we only train the linear classifier on top of them. So we start with raw mammograms from one or more datasets, and each image is passed through the encoder of the foundation model, which will map the image to a feature vector in its embedding space. And then we train the simple linear classifier on the feature vectors to predict labels such as healthy, benign, and malignant. So we have three different views here to explore the variability in the datasets and to see how this can lead to bias and cases of unfairness in classifiers on the image space, on the embedding space, but also on the classification outputs. So I'll start with the variability in mammography images. So in the slide, we can see examples of mammogram that are randomly sampled from each dataset. So we had 10 datasets. And we also have the average intensity histograms for each of the dataset. First, visually, there are clear differences in terms of contrast, breast positioning, but also appearance. And this actually reflects different scanner, but also different acquisition types. For instance, we have two data sets that were obtained from screening films, which is different from other data sets that have been acquired with digital mammography. And we can see here in the histograms that there are significant systematic shifts in the intensity distributions, and the data sets also differ in terms of population characteristics and disease prevalence. And all of this makes consistent performance across data set inherently challenging. So when we passed all the images through a foundation model and we look at the embeddings of this foundation model, the variability actually persists in the feature space. Here you can see the t-SNE visualization of 50 samples from each dataset across different foundation models. So here MammoClip, PubMedClip, and the others. And we can see that the different models, the different foundation models, they exhibit different embeddings. But overall, the data are mostly clustered by datasets, with here in red and blue, the two datasets acquired with film screening and not the rest by digital mammography. And we also see that there are some clustering by laterality here with Gloria, for instance, which is related to the way the model was pre-trained. But yeah, in most foundation models, we can see that the data are still, like the feature vectors, still encode a lot of domain-related information, like where the image comes from and how it was acquired, and not only the underlying pathologies. So we can suppose that linear classifiers trained on top of these embeddings will easily exploit such domain cues. And so this is what we did. We trained and tested linear classifiers on these features. So I will present here the results of all foundation models, but for the rest of the presentation, I will mostly focus on MammoClip. So when we train and test the classifiers on features from the same dataset, the performance is reasonably good for most foundation models. This is the first line, internal. But if we train on data from other datasets, we can see that performance drops substantially. And the size of the drop depends on the dataset pair, but also the model. And the pattern is actually quite consistent because cross-dataset generalization is much weaker than within dataset performance. And so one simple idea to improve robustness was to actually aggregate datasets. So instead of training the linear classifiers on features solely from one dataset and applying it to the other, we grouped all the features from all the dataset and tried to train a single unified classifier. And so on average, we found that aggregation improves the performance because the mean F1 score was higher than for many individual dataset classifiers. Especially, so here it was for the task of classifying healthy, benign, and malignant samples. And so we found, yes, that the average performance was higher than individual classifiers, but when we look at each dataset individually, the unified model performs worse than the model that was trained only on this dataset. So aggregation increases the overall performance, but it does not guarantee that every group will benefit from this aggregation. And this notion of different benefits across groups, here, datasets, leads us to fairness. To assess fairness, we treat each dataset as a group, and we ask, for a given label, what is the probability that a sample from this group is correctly classified. For instance, here, if we focus on healthy cases and compare RSNA and MMD to the others, we can see that healthy samples from this dataset are classified correctly much more often than the healthy samples from other datasets, which are usually smaller or less represented. And this actually shows that the aggregated dataset systematically favors certain domain, and typically these are the ones that contribute to more samples and or are closer to the pre-training distribution of the foundation model. And when we extend this analysis to different classification tasks, such as breast density, where we had more balanced sample within each dataset, we observe that the model gives more fair outcomes across datasets. This seems consistent with our hypothesis that domain-related information are encoded by foundation models, which provides a source for learning spurious correlation, especially when classes are imbalanced. And in such case, the easiest way for the model to reach a good performance is actually to predict the majority class per dataset. And so to address these disparities, we compared two families of strategy in the frozen feature settings. The first one is domain invariance methods, such as DINN, so adversarial learning. And the goal of these strategies is to limit the influence of domain-specific features during training. The second one was more related to fairness, because the idea was to optimize for similar performance across subgroup so that no dataset or class is disadvantaged. And in our experiments, we found that domain invariance methods do reduce disparities in performance and reduce unfairness, but often at the cost of performance. But what we found is that fairness-aware methods, and in particular group DRO, seemed to be more effective at making performance more uniform across datasets and class, while also keeping a performance drop relatively controlled. And so to conclude, what we found here was that modality-specific pre-training of foundation models and aggregation of multiple datasets are beneficial for overall performance, but they do not remove bias. Foundation models still encode a lot of domain-related information, and linear classifiers on top of them obviously can inherit these biases and amplify disparities across subgroups. And so we found that domain adaptation strategies can partially correct for this, but this may be sacrificing performance. So this suggests that current foundation models often encode more image-related information than task-related information in their embedding, which is quite problematic if we want to use them in a frozen feature setting. And so we found that fairness-aware strategy seem to offer a promising path. But right now, we need to see for better pre-training data curation, more diverse mammography cohort, but also more standardized fairness evaluation whenever foundation models are deployed, because such techniques does not ensure fairness and performance. That's all for me. Thank you for your attention, and feel free to read the paper if you're interested.
Perfect. Thank you so much, Elodie. I think we just running a little bit over time, so maybe we can take some more questions in the Q&A. But thank you so much, and for taking time today. So we appreciate it.